Hello everyone, welcome to the third video of week 3. In this video we will discuss one of the standard tests in statistics, the one-sample t-test. Now let us illustrate this test with the following example. In 1868, a German physician by the name of Karl Wunderlich reported that the mean temperature of healthy adults is 37 degrees Celsius or 98.6 degrees Fahrenheit. Nowadays, most people still consider these values as normal. Now let us revisit the findings of Wunderlich and compare them to the more recent measurements of the body temperature. Perhaps measuring devices have become more accurate in the last 150 years, or perhaps the mean body temperature of healthy adults has changed for some reason. We wish to test whether the mean body temperature of today's healthy adults is equal to 37 degrees Celsius. To perform the test, we use a dataset consisting of body temperatures measured among 130 healthy adults. Now, the histogram and the QQ plot of the observations suggest that the normal distribution is a suitable candidate to model the observations. So, we model the dataset as a realization of independent random variables with a normal distribution. The parameter mu of this distribution represents the true mean body temperature of today's healthy adults. We want to test the null hypothesis mu equals 37 against the alternative hypothesis that mu is different from 37. Now, the first thing we need to do is to find a test statistic that we can use to decide between the two hypotheses. Well, since mu is the expectation of the model distribution, according to the law of large numbers, the sample mean will be close to mu no matter which of the two hypotheses is valid. This suggests that we can use a test statistic based on the difference between x bar and 37. Since the sample mean is close to mu, realizations of x bar minus 37 close to 0 are in favor of the null hypothesis. On the other hand, realization of this difference far away from 0 are in favor of the alternative hypothesis. Now, does this mean that the difference itself suffices as a test statistic? Well, for our dataset, we find the value 36.8 for the sample mean, so that the difference with 37 is equal to minus 0.2. Now, how should we interpret this difference? Well, if the standard deviation of x bar minus 37 would be a quarter, say, then its density would look like the blue graph. In that case, minus 0.2 is not exceptional. On the other hand, if the standard deviation of x bar minus 37 would be 1 over 20, say, then its density would look like the blue graph in the right figure. In that case, the value minus 0.2 is an exceptional value. So this illustrates that we cannot take x bar minus 37 itself as a test statistic, but that we must consider this difference relative to its standard deviation. Well, let us determine this standard deviation. We first compute the variance. Because 37 is a non-random constant, the variance of x bar minus 37 is equal to the variance of x bar. And according to the rules for the variance of the average is equal to 1 over n squared times the sum of the individual variances. Since each xi has the same variance, sigma squared, we find that the variance of x bar minus 37 is sigma squared divided by n. And so the standard deviation is sigma divided by square root n. Now, to consider x bar minus 37 relative to its standard deviation means that we have to divide this difference by sigma over square root n. However, since sigma is unknown, we replace sigma by the sample standard deviation as n. This leads to the following test statistic for the null hypothesis. Well, let us find out which values of t are in favor of the null hypothesis and which are in favor of the alternative. Values of t close to 0 correspond to x bar close to 37, so these values of t are in favor of the null hypothesis. On the other hand, both large negative values as well as large positive values are in favor of the alternative hypothesis. Well, for our dataset, we find sample standard deviation 0.41, so that the value of t is equal to minus 5.45. This is clearly different from 0, but the question is whether it is extreme enough to reject the null hypothesis. To answer this question, we compute the corresponding p-value. Well, recall from the first video of this week that the p-value is the probability of finding an outcome of t that is more extreme than the observed value in the direction of the alternative hypothesis. Clearly, values to the left of minus 5.45 are more extreme, but in view of the alternative hypothesis, the value plus 5.45 is equally extreme, and values to the right of it are also more extreme. This means that the p-value is the sum of these two probabilities, which should be computed under the assumption that the null hypothesis is true. In order to do so, we first need to know what is the probability distribution of t under the null hypothesis. Well, in our example, the observations are realizations of independent random variables with a normal distribution with parameters mu and sigma squared. You have learned from probability theory that in that case, the sample mean also has a normal distribution, but then with parameters mu and sigma squared over n. This means that if we standardize x bar by subtracting its expectation and dividing by the square root of its variance, the standardized random variable has a standard normal distribution. Our test statistic is of this form, but with sigma replaced by Sn. The distribution of this random variable will no longer be standard normal, but something else. Now, to formulate what this distribution is going to be, we first need to introduce the following continuous distribution. A continuous random variable has a t distribution with parameter m if it has a probability density on the whole real line given by this expression for f. We denote this distribution by t brackets m. The parameter m is typically an integer greater than or equal to 1 and is called the degrees of freedom. And furthermore, km is a normalizing constant to make sure that the density has area 1 under the curve. There is an explicit expression for km, but we do not need this for our purposes. Now, from the expression of the density, we see immediately that it is symmetric around 0, since it has its value at x and at minus x are the same. For m equal to 1, it turns out that the normalizing constant k1 is equal to 1 over pi. And in this case, you may recognize the formula for the density of the Cauchy distribution. On the other hand, when m tends to infinity, then the expression of the density converges to that of the standard normal distribution. Therefore, a t distribution is somewhere between these two extremes. The density is symmetric, around 0, and it is bell-shaped, like the standard normal. The distinguishing feature is that the densities of the t distribution have heavier tails. The density goes to 0 more slowly than the standard normal density as x goes to minus or to plus infinity. Now, what this distribution has to do with our situation is explained by the following theory. Suppose we have independent random variables with a normal distribution with parameters mu and sigma squared. Then the ratio of x bar minus mu divided by Sn over square root n has a t distribution with parameter m equal to n minus 1. Now, this theorem enables us to compute probabilities for ratios like the one in the theorem by means of the t distribution. Okay, so let us return to the body temperature example. Our dataset is a realization of independent normal random variables, so the theorem holds. The expression of our test statistic looks very similar, but is slightly different from the ratio in the theorem. However, when the null hypothesis is true, then the two expressions are the same. This means that in that case, the test statistic has a t-distribution with n-1 degrees of freedom. Now recall that the p-value to compute is the sum of these two probabilities. And since these probabilities are computed under the null hypothesis, they can be computed by the corresponding probabilities for a t-distribution with n-1 degrees of freedom. The question remains, how do we compute probabilities for a t-distribution? Well, having seen the expression for its density, this will be far from trivial. However, R has a function that does this for us. The R function pt computes left-tail probabilities for the t-distribution. Now, using that n-1 equals 129, the first probability can be computed with pt itself, and the second probability with 1 minus pt. Running this R command, we find that the p-value is 2.5 times 10 to the power minus 7. This means that if the null hypothesis is true, one finds the value minus 5.45, or a more extreme value, in about 2.5 times out of 10 million. I guess you agree that this is so small that we can reject the null hypothesis. We conclude that the true mean body temperature of today's adults differs from 37 degrees Celsius. Now, the previous example is a special case of testing whether the parameter mu of a normal distribution is equal to some given value. This type of test is called a one-sample t-test. More about this test in the next video. See you then.